Turing machine.
This video is subject to copyright owned by Nile University. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
Turing machine. In Turing machine, we have to understand the hierarchy of languages. So we basically have the set of regular languages. Then we have a set of context-free languages. The question will be is what is the term of omega omega to the power r, and what is the term of ANPN. Now the other question will be is what are these terms here, which is omega omega, and what are a to the power n, b to the power n, cn. So languages accepted by the Turing machine are superset of the regular language, context-free languages, and the Turing machine languages. So to understand the Turing machine is we assume we have a tape, and the tape will have a read-write head. The tape will be sequential, and there is a control unit or a logic or a state diagram, and this state diagram will read from the tape, and then it can impact the tape by advancing or by writing. Now the assumptions are that the tape itself has infinite length, so there is no boundaries, and the head can read write, and the heads can move left and right. These are the assumptions. However, if the head will move to one direction, this will end up to be a push down automata. So we have to understand here that the head can go forward and can go backward. So the head at each transition or time step, it can either read a symbol, write a symbol, or move left or move right. So an example here is this head, which can read symbol A, then write symbol K, then move left to location B. So it reads A, it writes K, and then it moves to the left. When the head moves, we will consume this as a time. Here is another example where it reads B, writes F, and then move right. So an input string will be the input strings, and this symbol here represents blank symbols. So the input string will include symbols, and then the blank ones will look with the diamond. So the head can start at the leftmost position of the input, and then it can move. State and transitions. So I can read a symbol, I can write a symbol, and it can move left. It can read a symbol, it can write a symbol, and then it can move right. And then it moves from state to another. So an example here is at time 1, the current state is Q1. It reads the symbol A, it replaces A with B, and then it moves right. So it reads A, it replaces A with B, and then it moves right to read the next one. So this is the example which we have here. If it moves here, and then this will be at time 1, and I have a blank to be G, so the blank here will be replaced to G, and then it moves right. Determinism. Turing machine are deterministic. So when these are deterministic, remember that if you have a state, it moves based on specific symbols to as a next state. However, these symbols cannot be similar. So if it's Q1 and I have symbol A, it reads A, it converts it to B. And if it's Q1 and I treat symbol B, it transfers it to D, and then it moves L. And then it will become it from Q1 to Q3. There is no empty transition allowed, which means you have to read or write before the transition. So a transaction, like if it's A, replace A by B, or A replaced by D, and then move, this is not allowed, because these basically are confusing, or it generated non-deterministic output. Partial transition, no transitions from the input symbol C. Here is our partial transition. So I have A, I replace it to B and go R. I have B, I replace it to D and go left. There is no transition for input C, for example, so C will be the terminal. Halting. Halting or halt is when the machine there is no transitions to follow. The machine will stop. So basically, no transitions from Q1. All Q1 will receive input. There is no arrows are coming out from Q1. So Q1 is a halt, or basically is the end state, or it will stop. Here another example. So there is no from Q1 and symbol C, it's a halt because there is no input. If Q1 reach C, there is no halting. Accepting states are states which will end up as terminal. So no outgoing transition from the accepting states, and not allowed is when you have accepting states going to a transition. We will accept input string if the machine halt in an accepting state, and it rejects input string if the machine halts in non-accepting states or the machine enters in infinite loops. In order to accept an input string, it is not necessary to scan all the input of the input string. So Turing machine example, if I have the alphabet A and B, and I accept the language A star, which basically I can repeat A. So basically I will have the initial state Q node. As long as I have A, I replace it with an A and I move right. And once I have a blank, I will replace it with a blank and move left. And this will end up having Q1. So here, this will be an example. So at time 0, it will accept A. Once it reaches that, it knows its end, so it moves back, it halt and accept. So a rejection example, if I have A, B, now B cannot go anywhere. So basically it halts and reject. A assembler machine for some language for the input alpha of a subset alphabet A, accept language A. So basically if I accept language A star, here's an example. So here I accept the first input A and I will stop at the first Q node. Infinite loop example, in the Turing machine for languages, I will have A star plus B parentheses A plus B star. So I will have here the production rules. A lead to A and R, B lead to B and L, and star lead to, space or empty lead to empty and L. And here is the state. I will move to Q node, and here I will go to Q node, and then it keep going. So every time it keep going, because an infinite loop, the acceptance state cannot be reached, the machine never halted, the input shall be rejected. Another example of the Turing machine for the language A to the power n, B to the power n, where n greater than 1. So I have here the initial state Q and node, and the Q node can go, if it's A, it will go to Q1, if it's Y, it will go to Q3, and then blank, it will halt, and if it goes to Q1, it will give to Q1, then it turn back to Q2, and then it give. So the machine matches A with B, and it replaces the leftmost A with X, and finally the leftmost, and replace it with Y, until there is no more A's and B's. There is no remaining A and B to reject. So here is the example. At time 0, we stand here, we keep going, moving, and then it keep going. The observation, if we modify the machine language for the language A n to B n, it's easy construct machine for the language A n, B n, Q n. Formal definition for the Turing machine, you have the function of Q1 and A, which will equal Q2 with replacing B and moving an R. The transition function of Q1 and C, Q2, D, and L. For the Turing machine formal definition, I will have the machine M. You have the states input alphabet, tape alphabet, transition function, initial state, blanks, and accepting states. In the configuration, the instantaneous description will be CAQ1BA. and here is the move will become from q to xayb to word xq node ayb, and this yield in one move, and then you do the computations. So the Turing machine is accepting a language which accepted by a Turing machine language. You have an initial state, a set of production end up accepting states. If a language L is accepted by a Turing machine, then we say that L is a Turing recognizable. Other names is Turing acceptable, recursively enumerable. To summarize it, Turing machine is a special set of machines, one of the early machines that have been defined. It puts a special constraints and special conditions on how we can understand the grammar. From Turing machine perspective, is a special case of machines. It has been the foundation of computers. You need to understand it as an example of how to get regular language to context-free language to Turing machine language. If you have further questions, please let me know via email or by the notes below, and looking forward to see you again in the next lecture.